All right, so it's the average kinetic energy. There are 3 temperature scales. Which one will we not use in this class? Fahrenheit, okay? We don't use that. We will use Celsius or Kelvin. So while we're reviewing some, it's page 2 in your packet. While we're reviewing some, guys, how do you go between Celsius and Kelvin? To what, though? You add 273 or subtract it, but to what? That doesn't tell me anything. What temperature? There's 2 values right here. There we go. K equals degrees Celsius plus 273. Now, do you have to memorize that formula? No, guys. Get your reference packets out because you're going to need them today. We're going to cover the last equations that are in our reference packet here today. So get those out. Calorimeter, folks. It is one of your vocab terms. It's a device that is used to measure the energy changes. It measures heat absorbed or released in a chemical or physical change. It is not the same thing as a thermometer, like it says in your notes. Thermometers, folks, they will measure temperature changes, but not energy changes. Now, a calorimeter does use a thermometer within it, but it's not the only thing that it uses. A classic example is what's called a bomb calorimeter, where everything is inside, and you go through basically kind of burn whatever it is in there to see how much energy is released, and you go through a calculation, and you figure out how much energy was absorbed or lost. And then heat or heat energy is the sum of the total kinetic energies of the particles in a sample of matter. Our units we use are joules or calories. Heat and energy, guys, they mean the same thing. Okay? They're kind of synonymous with each other. The variables, however, are different. So heat is either a lowercase or capital Q. Don't get hung up on it, folks. They mean the same thing, whether it's a lowercase or a capital Q. E, capital E, we know that's energy. We've seen that before. Okay? Then there's the joule and the calorie. Joule is just a capital J. Calorie is CAL. 1 calorie equals 4.184 joules. You do not need to memorize this conversion factor. We're going to do an example here in just a second with it, but I will give this to you on a test or a quiz if you need it. Fun fact of the day, food calories are actually kilocalories. So when you look on a bottle of soda or a bag of chips, and this says like 150 calories, that's actually kilocalories. What does kilo mean? 1,000. So really, there's 150,000 calories in that drink or in that bag of chips. Now, I don't say that to freak you guys out, okay? To say, oh, I need to go on a diet or whatever. My point in sharing this with you folks is to tell you and show you that's how much energy your body needs to function. Okay? Food calories are kilocalories. They say that, average diet is like 1,500 to 2,000 calories, somewhere in that range, depending on your size, per day. So that's really 1.5 million calories or 2 million calories that your body needs. Again, those are units of energy, guys. That should show you something as to how much energy your body needs to function. All those metabolic processes and whatnot that are going on without you even realizing it, your body needs a lot of energy. Okay? Fun fact of the day. All right. Here we go. Here's our example conversion going between calories and joules. It says, how many calories are in a potato with 686,000 joules of energy? What's our first step? So what should we do first? Given. Always start with a given, folks. You should know that by now. So we've got joules. Okay, we're trying to go from joules to what? Calories. Where does joules have to go? On the bottom, right? Because we're going to cancel it out. On the top then would be calories, CAL. Joules are canceled out. Now, go back to that conversion factor that we had. 1 calorie equals 4.184 joules. Go ahead and do the math. When you do the math, how many you get? Should be a big number. 957? Point what? So 0.9. That's a lot of joules there, folks. Now, if we were going to go to correct sig figs, how many sig figs do we have in our original number? Yeah, sorry, I did it in the last class too. It's calories. My apologies. Good looks there. All right. 3. There are 3 sig figs, folks, in that first number that we had. 6, 8, 6. Those are the significant figures right here. So we need to have the same amount in this one. So that's going to be right here. How would we round that? Look here. How do we round to 9? It goes where? Up. So we would have 164,000 calories. Okay. Now some more reviews. We're going to throw a review in here over the next few weeks. You may not even realize we're doing a whole lot of review, but we are. 164,000 calories. Let's say I want to get that to kilocalories. How do I do that? So here, multiply and divide. Set up your T-chart, folks. Calories will go on the bottom. Kilocalories will go on the top. Now, think back to Unit 1 with those prefixes. Which one always gets the number 1? The prefix always gets the number 1. So 1 kilocalorie has how many calories in it? It's got 1,000, or 10 to the third. So we're dividing by 1,000, guys. So this is going to have 164 kilocalories. Equation. First one we're going to talk about, guys, is specific heat. Specific heat, by definition, states it's the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. How can it be 1 degree Celsius or 1 Kelvin? How can that be? They're the same, guys. The increments are the same. 1 degree Celsius equals 1 Kelvin. So if you change something by 1 degree Celsius or 1 Kelvin, you're changing it either scale by the same amount. Okay, and that's a big key concept right there. Some of us missed that on one of our old tests where it said, if I change something by 10 degrees Celsius, how many degrees Kelvin? Everybody's like, oh, I got to convert it by 273, blah, 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 all that stuff. No, folks, if you change something 10 degrees Celsius, you're also changing Kelvin by 10 degrees. Their increments are the same. So specific heat values are usually measured under STP conditions. What's STP? Standard temperature and pressure. Do you have to memorize those values? No. Where can you find them? Reference packet, first page. Speaking of the first page of the reference packet, flip there right now. The very front page of your reference packet. Your specific heat, folks, will be based on the substance that you're dealing with. Each substance has its own specific heat. Okay? So if you look at the table there, you've got one down below that talks about metals. All right, a bunch of different metals listed there. Specific heat is one of the attributes that is listed there along with density and melting point. Then look right above that table, guys, you've got a bunch of thermodynamic constants. And those are dealing with water. We'll talk about heat of fusion, heat of vaporization later on this period. But you also have the specific heat of water. How many specific heats of water do you have there? 3, right? What's the difference? Besides their numbers, what's different about them? State of matter, right? There's one for liquid, there's one for solid, there's one for gas. You guys have to be able to determine and know which one we're dealing with within a problem. What's the biggest indication as to how you might understand what state of matter you have present? What's the biggest indicator within a problem? Okay, subscripts, if they give you subscripts. Maybe they won't. Absolutely we can use subscripts. What if they don't give you subscripts within a reaction? What'd you say? Temperature, folks. You guys all should know because your favorite lab of the entire year, right, where you guys took ice and you melted it and then you heated up the water and you boiled it. I can see it on your faces. You guys loved it so much. All right. But guys, you should know the temperatures. If X is less than 0 degrees Celsius, what do you have? A solid. If X is greater than 0 degrees Celsius, but less than 100 degrees Celsius, what do you have? Liquid. And if X is greater than 100, guys, X is just a temperature. If X is greater than 100, what do you have? You have a gas. Maybe you should jot that down just so you have it there for reference. Specific heat, folks. There are 3 formulas that we are going to talk about here today. This is the first one. This is on, if you look on the formula page in your reference packet, so flip there now, formula page for your reference packet, you'll see it's kind of in the middle. It's one of the last three formulas that we need to talk about before our final. Q equals MC delta T. Folks, if you forget what these variables stand for, they define them for you on your formula page. Okay? So they're right there. C, specific heat. Now, you may see it written in a few different ways. Like I have it up here, capital C with a subscript P. You might just see it as a C, like a capital C or a lowercase c. They all mean the same thing. Most likely, I apologize for this. You will see me write it like this, because that's the way that I learned it, is lowercase. It does not mean anything different, folks. It's the exact same as you see right here. Okay, it's just a different way. To be honest, I don't even know what that subscript P stands for. It doesn't matter, because it's not really significant. Okay? All you need to know is that C means your specific heat, and that's, again, a constant. You'll have to be given it, or you can look it up in your reference packet. Q, that's our heat gained or lost. That's in joules. That's the one new unit, folks, that you need to memorize or just be aware of, is that we measure heat or energy in joules. Mass is in grams. We've done that all year long. And delta T, what is that delta, that triangle? What does that stand for? Change, okay? And it talks about right here how we calculate our change, guys. Any change, whether it's temperature or volume, it's always final minus initial. That's the second time today I've said finus. I don't even know what that means. Final minus initial, okay? Final minus initial. And again, it can be either degrees Celsius or Kelvin. You take a note right here with this piece. You can have a negative value. You can have a negative value with this one with a temperature. Now, I'm going to say this. Don't answer it now. Think about it. Why? What is a negative temperature? What does a negative temperature tell us about our problem? Think about it. Don't answer right now. We'll come back to it a little bit later. So be thinking about that. What does a negative temperature mean in terms of heat and energy? Okay? Come back to it later. All right? All right, here we go. Let's take a look at a practice example. 4-gram sample. What is grams? What variable goes with grams? Mass. So mass equals 4.0 grams. A 4-gram sample of glass was heated from 0 degrees Celsius to 41 degrees Celsius. So I've got two temperatures. If I have two temperatures, what am I going to be looking for? Did we just say in our last slide? The change, right? Now, state is going to come into play. Okay, we'll see how that plays here. So we've got delta T is what we're going to look for with those temperatures. Well, how do I calculate delta T? Final minus initial. I almost said it again. Thanks for not mocking me too, by the way. I thought for sure somebody was going to say finus right there. Anyway, 41 degrees Celsius minus 0 degrees Celsius. What's that going to do for us? Nothing. Easy delta T to calculate. 41 degrees Celsius is our delta T here. Now, the last two pieces are the new ones that you guys haven't dealt with yet. Again, you can look them up. Joules. Maybe you don't know or you forgot what joules refers to, what variable it refers to. So we know it's either going to be Q or it's going to be C. So it says we're looking for the specific heat. Go to your reference packet, folks. On that formula page, look over there where they define variables. Look for specific heat. Which variable is specific heat? CP. I'm going to try my best to remember to write CP more than I will write C. So specific heat is what we're looking for. So that means joules has to correspond with what variable? Q. Q equals 32 joules. So folks, here's our formula. Q equals MC delta T. If I gave you an equation like this, A equals B, C, D, and I said solve for C, how would we solve for C? Yeah, divide by B and D on both sides. Piece of cake. Guys, it's the exact same equation. The variables look different. So how do we get C by itself? Or excuse me, CP by itself? Divide by what? M and delta T. They're gone there and there. Do it over here on the same side. Now it's just plug and chug. CP equals Q over M delta T. So plug in your values, 32 joules, all over your mass of 4.0 grams, and 41 degrees Celsius. Solve the problem. What do we get? 0.20 or 0.195. Now our units, can I cancel any of those units out? No, so I've got to leave it just like I see it, guys. Joules over grams times degrees Celsius. And that's a good unit. Even though it looks weird, it's a good unit because it states for every, it's that many joules per 1 gram degrees Celsius. You can round. If you had 0.2, that'd be fine as well. I'm not looking at sig figs too much. If we round the correct sig figs here, it would be 0.20. That's okay. Guys, but listen. By definition, these units are good because it says for every 1 gram, a certain amount of heat or energy needed to raise 1 gram of a substance by 1 degree Celsius. So in this case, our specific heat for this piece of glass, it takes 0.195 or 0.20 joules of energy to raise 1 gram of that glass by 1 degree Celsius. Okay? I want you guys to try example number 2 in your packet. So we are given mass, delta T we can calculate. When you calculate delta T and you set it up like so, what do you get for your delta T? Your change in temperature should be 72.2, I believe, degrees Celsius. Specific heat they gave you, and we are looking for Q. What do you notice, though, about your temperature and your specific heat? Different units, right? Well, here's Kelvin, here's degrees Celsius. So what do we have to do? We have to what? Convert it to... So you say no. Why do you say no? Guys, remember we just said before that if you change something 1 degree Celsius, you also change it 1 degree Kelvin. Okay? So it's the same. Because we're dealing with a change, you don't have to do a conversion at all here. You're going to leave it just as it is. We can just say that, oh, this is also 72.2 Kelvin because it's talking about change. When you change one by 1 degree, you change the other one by 1 degree as well. All right? So here we go. Let's just plug and chug. Q equals MC delta T. So Q equals 55 grams multiplied by 0.897 joules over grams Kelvin times our temperature, which is going to be 72.2 Kelvin. K's are going to cancel out. Grams are going to cancel out. We're left with joules, which is what we want for Q. When you plug all that in, 55 times 0.897 times 72.2, what do we get for a final answer? You guys are mumbling. Somebody raise their hand and say it louder. 3562 joules, folks. Now, if I were going to go to correct sig figs, what number would I look at? 2 sig figs because of our mass number being 2 sig figs as well. So, we could round this to Q equals 3600 joules. What type of change did those two problems show or reflect? Okay, so we're talking about energy, but raising the temperature, guys, the temperature change is what this formula is made on. Q equals MC delta T deals with a temperature change. Now, is everything going to be just a temperature change? Think back to that lab that we did. Was that only a temperature change that we investigated when you guys took the ice and you went all the way through it? States of matter, guys. So there's phase changes that we take place as well. That's where we come in with this heat of blank. So there's 2 heat of somethings, HF and HV. What does HF stand for? Heat of fusion. Okay, so that F means fusion. Now, if we think back, guys, we did introduce fusion back in Unit 10. Okay, fusion, what do you think it means or kind of relates to? Drew, you already said it. Freezing. Now, freezing is one thing that it relates to. What's the other thing that it relates to, do you think? Solidification or, well, freezing is solidification, same thing. But what's the opposite of freezing, folks? Melting. Okay, so they mean, guys, heat of fusion is referring to these two phase changes. What's the difference between the two? Don't tell me states of matter. Talk about energy, thermochemistry here. Nope. One is going to be endothermic and one is going to be exo. Guys, what does exothermic mean? Release heat. Endothermic then would mean gain it. Guys, one is going to release heat, one is going to gain heat. Which one? Again, think back to your example, guys, your real life example when you did this in the lab. Which one is which? Freezing means to do, let's start with melting. Melting means what? What are you doing with heat? Think back to the lab, folks. You took ice, you put it in a beaker, and then what did you do with it? You put it on the hot plate. What was the hot plate doing? It was applying heat. Guys, just adding. You were right the first time, Jonathan. Melting, you are increasing heat. Freezing, you are doing what? Losing heat. You're releasing it to the surrounding environment. Okay? So guys, fusion, the key terms that are going to guide you to whether you're going to use the HF constant or the HV is melting or freezing. Okay? HV stands for what? This one's a little bit easier to understand because the word tells you right there the phase change, where fusion is not a term of a phase change that's super common. Vaporization, guys, refers to what? Boil or condense. Now, let's go back to the same thing. If we boil something, what are we doing with the heat? We're adding heat to it, so it's positive heat. If we condense it, what are we doing? Releasing it, so we're taking heat away. Jot this down so you have, when we look at those values, heat of vaporization, 2260, heat of fusion, 334. This is why it takes longer for water to boil, because there's a lot more energy needed to break those intermolecular forces to then allow those molecules to separate out and become further apart. It takes a lot more energy. That's why it takes forever for water to boil, but not as much time for it to melt. Okay? Let's take a look at an example here. It says, calculate the amount of heat required to melt 55 grams of ice at 0 degrees Celsius. Let's write things down. What are we looking for in this problem? What variable? Q. We're looking for heat required, so that's Q. I'm given grams, which is my mass value, 55 grams, and I have a temperature that is 0 degrees Celsius. That's all I have. Do I have two temperatures here? No. So am I going to be using Q equals MC delta T? No, I'm not, because it's not talking about a change in temperature here. I'm talking about a phase change, not a temperature change. Now, there's a key word in this problem that's going to tell you which formula to use. Nope, not ice. There's a better keyword. Melt, folks. That's a term. Again, we wrote it right here at the top of this slide. That's indicative of a phase change. These four terms, freezing, melting, vaporization, boiling, or condensing, guys, they are telling you it's a phase change that's occurring. So you got to use Q equals Q equals MHF or Q equals MHV. Which one are we going to use in this problem? Q equals MHYF? Melt. Absolutely. So then, guys, we can jot down HF. That's 334 joules per gram. Am I going to use temperature at all? Nope. It's not going to come into play in my formula. Q equals 55 grams times 334 joules per gram. Do the math. So grams are going to cancel out. You should end up with 18,370 joules. That's a lot of energy, folks, required to melt 55 grams of ice. Questions about this problem? Easy? Math, guys, is not that hard. We've done a lot harder math. The hardest part is identifying what pieces you have and recognizing key terms. What's the first thing I got to do here with this problem? Well, how are we going to do that? See if it's a temperature change or not. By what? Writing down your given information. Okay, here we go. I've got, let's see, how many joules? So what am I looking for? Q is what I'm looking for. We've got a mass that is 5.0 grams. It says water cools from 75 degrees Celsius to 25 degrees Celsius. So there's two temperatures. Is that a temperature change or a phase change? Right? So guys, it talks about cools. Is that a phase change term? No. So we're going to use what formula here? MC delta T, because it's a temperature change, not a phase change. There was no melting or freezing term or solidification or condensing or vaporization or boiling. So delta T, how do I calculate delta T? Final minus initial. So I've got 25 degrees Celsius minus 75 degrees Celsius. What's that going to give me? Negative 50. Ooh. Can it be? It can, absolutely. Yes, it can. Now, what am I lacking, though, to solve for this formula? C. Where can I find it, though? Reference packet, folks. Get those out. So when you look it up, you've got three values to choose from. Why is it 4.18, Eric? How do we know that we are in the liquid state here, folks? Now, water is what everybody goes to, but that's not as strong of an answer because they could just say water at a different temperature. Right, guys, the temperature. You are between that window of 0 and 100, so you know you're in that liquid state. So our value is going to be 4.18 joules over grams degrees Celsius. Now it's just plug and chug. Negative what? Negative 10.5? 1045 what? Joules. Now, here's coming back to that question, guys. Negative temperature, what does that imply? You are losing energy, guys. So we are cooling something down. When you cool something, you release heat. So a negative temperature. This is what a negative temperature means, because you're going to end up with a negative Q. A negative Q value means you lose heat. A positive Q means you gain heat. So negative Q equals release heat. Positive Q means you gain or absorb heat. Can't you just tell that? It says, how many joules does it take to melt 35 grams of ice at 0 degrees Celsius? What am I looking for? Q is what I'm looking for. What's my key word in this problem? Melt. What does that imply right there, folks? Phase change. So what formula am I going to use? Am I going to use Q equals MC delta T? No. It's going to be MH what? It's going to be MHF here because we are dealing with fusion. Go ahead and solve this problem. All right, so this is how you should set it up. Plug it in. What do you guys get for an answer? What? 11690. Lots of energy right there, folks. If I wanted to go to correct sig figs, how many sig figs would I report to? 2. So that would be right here. I'm going to look at this number. Does that go up or down? Up. So my Q value would be 12,000 joules. Questions at all, folks? Your homework tonight. Finish numbers 3, 4, and 5 in the packet there. Page 548, numbers 16 and 17.